Okay, so today I will talk about quiet sun magnetism, and just as a brief introduction, what is it? So this is a magnetogram, HMI magnetogram. You do see here a few active regions, and you see these more diffused active regions, which might be active region which decayed a while ago. But if you go far away from active region, you see on the solar surface a lot of these small-scale salt and pepper fields. This is what solar physicists normally refer to as a quiet sun. But I hope I'm able to convince you it's not as quiet as it looks. And the first indication for that is if you estimate the total unsigned flux, which is in these quiet sun regions on the tau-1 surface, it's about a few times 10 to the 24 Maxwell. And that is about you take all sunspots of an 11-year solar cycle, you shred them up into tiny pieces and disperse them over the solar surface. This is what the quiet sun is at any given time. That kind of gives you an idea. There's actually a lot of energetics going on here. This magnetic field is quite significant in a global context. So what I would like to talk about here is a little bit where does this magnetic field come from, and that has been looked at not only from theoretical investigations. There has been a lot of investigations based on observations, and people found it doesn't really vary with the solar cycle. It doesn't really, the strength of the quiet sun doesn't really depend on the nearby network field, which is a strong suggestion it's independent from the large-scale dynamo. There has been a lot of work using turbulent fluctuation dynamos to explain quiet sun magnetism. The one question I specifically would like to answer here, or address at least, is where is the small-scale dynamo located? Sometimes you read in the literature terms like local dynamo in the photosphere. Does this make sense at all? Or is it also a small-scale dynamo distributed throughout the convection zone? In particular, I would like to point out a few aspects where actually we can look at observations and see the difference between dynamo action just in the photosphere and contributions from the deeper convection zone. And if you're not working with the sun, I also would like to remind you that the sun is likely the only place in the universe where we can at least observe some aspects of small-scale dynamo action. In most other objects, it's hidden by insufficient resolution. So here, just a brief history of some simulations of small-scale magnetism. I would like to highlight this paper by Bob Stein in 2003, where he for the first time pointed out that there's very little recirculation in the photosphere, so it makes sense to think about always of a global dynamo, even if you think about small-scale magnetism. Now, in the following years, 2007 was the first time when there was a realistic simulation. Realistic, I mean you include radiation transport and really get most of the physics in the photosphere right. So the first simulation of that kind was done by Vögler and Schüssler in 2007. And they actually deliberately, they used the setup to kind of restrict the dynamo action really to the photospheric levels. This has been compared to observations, and they found that this simulation only can explain about 50% of the magnetic field we do observe in the quiet sun. The only way, at least when I got involved in this, to actually get the saturation level up is to have a small-scale dynamo which accounts for the fact that there is a deeper convection zone, there is dynamo action in the deeper convection zone. And with this recirculation, one can get finally to values which are consistent with observations, and the values are something about 60 to 80 Gauss mean vertical field on tau=1. In terms of RMS, it's somewhere 180 to 240 Gauss, or 1/3 of equipartition at tau=1. And very recently, there has been also another paper which looked at the Hanley effect. The Hanley effect is very interesting since it doesn't have any cancellation issues. It really sees turbulent magnetic field regardless of the orientation. And those recent observations and the interpretation is also kind of consistent with what has been previously inferred from the Zeeman effect. I will present here a few simulations, and these are radiation MHD simulations. The photosphere is modeled with MHD, 3D radiative transfer, open equation of state. Some of these models I show, they reach up into the corona. They have a simplified chromosphere. The corona is then modeled with field-aligned heat conduction, optically thin radiative loss, and they have no explicit heating model. So basically, the corona is heated by dissipation from the MHD code. And the code is the Muram radiative MHD code. So how do these small-scale dynamo simulations look like? This is an example of a high-resolution run. This has 4 kilometers grid spacing. I show here the vertical intensity of bolometric intensity. This is a magnetogram at tau equal 1. On the vertical slide show the vertical velocity and the magnetic field strength. And this is a simulation which agrees in terms of what we know from Zeeman, polarization, and Hanley effect with the strength of the quiet sun field. Now, the bottom boundary condition, you kind of can, by looking at this movie, imagine it's an open boundary, so it actually is very sensitive to what you do at the bottom boundary, which kind of mimics that the convection zone is actually deeper. So if you do simulations with different bottom boundaries where you can either enable or disable deep recirculation, you kind of get 2 classes of solutions. So here I show the vertical profiles of equipartition field strength in these runs, as well as the RMS field strength when the dynamo is saturated. And if you do use bottom boundaries which do not allow for deep recirculation, typically the field strength is about half of what it is when you allow for the deep recirculation. And no deep recirculation are boundary conditions which are open, but in inflow regions the magnetic field is 0, whereas with deep recirculation, this could be either open boundaries where you allow for the presence of horizontal field in inflow regions, or you actually use a truly closed boundary condition, which is a blue line in this case. Now, this is just a number we already know. If you compare this to observations, that only the runs with deep recirculation actually agree with observations, but are there other observables we could look at? And I would like to focus here on 2 aspects, the subgranular scales and supragranular scales. So at subgranular scales, I would like to focus here on something which is called exploding granules. These are essentially granules which grow so large that they form a new downflow lane in their center. And from the standpoint of a dynamo, this might be interesting because this is kind of the most pristine condition you can find in the photosphere, where you kind of restart the field amplification process. Since the center of granules normally have the weakest field. What you do see here, you form mostly initially a thin layer of strong magnetic field, and turbulent magnetic field kind of boils up a little bit later on one side of this new downflow lane, which kind of happens right here. And I slowly step through this movie here in this plot, where I show different stages of the field amplification. First, you just see an amplification of the seed field which is present in this granule, which leads mostly to a very coherent field. You see very little turbulence. When you look at the intensity image, you actually start seeing that one edge of the adjacent granule becomes sharper than the other side. And it's actually this side which has the sharper edge, where at later points you see the turbulent magnetic field showing up in the photosphere of the sun. And what actually happens here is, if you look at the cross-section, is that you have asymmetric horizontal vorticity. Typically, these newly formed downflow lanes, they kind of wrap up in either the one or the other direction. And having this vertical flow leads to this sharp feature in the intensity, which has been first found by Oskar Steiner in a paper in 2010. And this leads to some turbulent field amplification very shallow to the surface of the sun, only 200 kilometers depth, and that is brought up within about a minute or 2. And that's the reason how that's the way how the first turbulent field actually shows up in the observable layers of the photosphere. Initially, this newly formed downflow lane is a pretty laminar, just converging flow. So what does this have to do with deep and shallow recirculation? Now, this is an example of really shallow recirculation. So what is the role of deep recirculation here? So you can take advantage of these dependence on the bottom boundary condition and set up simulations which either have deep recirculation or don't have it. And here I show on a logarithmic scale the vertical and horizontal feed on tau equal 1. This is the case with deep recirculation. This is the case with only shallow recirculation. The case of deep recirculation, you have a more coherent initial seed feed in the granule, which leads to this amplification of these strong magnetic sheets. If you don't have deep recirculation, actually most of the granule is almost completely feed-free, and all the feed you're having is the one which comes up from shallow recirculation. So you have only the turbulent component without these more coherent sheets. So this is something you can distinguish these two processes and can look for it in observations. Now, looking for that in observations so far, I think, has been pretty borderline, and the reason for that is, particularly if you look in these exploding granules, these turbulent feed is really only visible in the deep photosphere. If you just go a scale height or two higher, you don't see anything of it. So your best chances to observe this is in the deep photosphere, and if you want to look very deep in the photosphere, in the case of the sun, you have to go somewhere to 1,600 nanometers where there's the opacity minimum, and then you would lose a lot of resolution. So this is a good science target for the new Daniel K. Inouye Solar Telescope, which is currently built, which has a 4-meter diameter. So you get actually a lot of benefit of resolution from the bigger telescope. So this is kind of a science target which one could address with a telescope maybe in a few years from now. Now, another aspect of this deep recirculation I would like to focus on is when we look now at the larger scales. Now, these are, again, small-scale dynamo simulations. They differ in the sense that they are now much wider boxes. They are 98 megameters wide, 80 megameters deep. And again, I used a setup without deep recirculation. Here, two setups which implement deep recirculation through different bottom boundaries. What I would like to point out here is, again, you see a difference in the saturation field strength, which is shown here by the solid lines, again, by about a factor of 2. But in addition to that, you kind of start seeing an organization of the magnetic field on larger scales. You see something which looks like emergence of small bipolar regions. They might be called ephemeral active regions on the sun. You start forming some network structure on a scale like supergranules, and it actually leads to a larger scale flux imbalance, which is shown here, which reaches values of 5 to 8 Gauss on a scale of a supergranule on the sun. So is this realistic? No, this is actually a quiz slide for you. This is 2 magnetograms. One is taken from one of these simulations. One of them is an actual observations with Hinode. They are both horizontally the same size. Do you have any idea which one is which? Okay, you have seen a lot of real sun. That's actually pretty good. The only reason you can tell them apart is you see a little bit more small-scale stuff here in the simulation than in the observation. But this is a Hinode scan during it was close to the last solar minimum. And the flux imbalance on a scale of 25 megameters, a quarter of the domain, is about 5-6 Gauss here, quite comparable. You can also do this in a comparison in a more statistical sense. This is a method Scott McIntosh introduced a while ago, which is these magnetic radii of influence. So essentially what you do in a magnetogram, for each pixel, you kind of determine a circle, how far do you have to go out until the flux is balanced, and then you make a histogram, how many of those you find as function of scale. Now the small scales here in observations, they're impacted by telescope resolution, and in the case of simulations, they're impacted by the resolution, of course, of the simulation. But if you go to scales larger than granules here, this is a region which is here interesting. You kind of see the same slope in both cases. So this organization of flux imbalances on larger scales comes out pretty nicely in these deeper small-scale dynamo simulations. And this is important if you actually want to maintain a corona in a quiet sun. Now, this is now one of these simulations, which in addition to the photosphere, actually they go up into the corona. Here I go total of a little bit more than 40 megameters above the photosphere. So what I show here, this is synthetic emission in different AIA channels. So this is EUV radiation from the corona. You can compute the total radiative loss from the simulations. It's about 6 times 10 to the 5 ergs. per square centimeter in second, which is at least within a factor of 2, what is typically estimated for the quiet sun. So this large-scale flux imbalance leads also to the right amount of energy fluxes to maintain a corona. And if you switch back to a dynamo model which only has the shallow recirculation on the same scale, the corona looks about a factor of 50 or 60 dimmer. If you compare them side by side, here just horizontal averages of the RMS field strength. As I mentioned before, in the convection zone, there's about a factor of 2 difference, but by the time you go into the corona, since of course the large scale matters if you want to go higher up, then you have something like a factor of 10 difference in the magnetic field there. And that makes a big difference. You still get a corona in the shallow recirculation case, but it has only about 500,000 Kelvin, whereas in the other case, it reaches between 1 and 2 million. It depends a little bit what you do at the top boundary. So this deep recirculation also manifests itself on the large scales, and this is crucial if you want to maintain a corona, even in the case of a quiet sun when there are no active regions. Now, in the end, I just would like to highlight a few additional energetics of these small-scale dynamos. Since already pointed out, there's a lot of magnetic energy actually compared to a large-scale magnetic field in there. So this shows energy conversion rates in the uppermost 1.5 megameters. The dominant driving term of pressure buoyancy driving, which is the solid blue line, most of this goes into downward acceleration of fluid. If you add these two together, you get the black line, which is the total amount of energy which is available to drive turbulence and to drive a dynamo, which is about 150 ergs per cubic centimeter in second. So the question is, how much of that is actually needed to maintain the small-scale magnetic field against ohmic decay? And this question cannot be answered without actually discussing the magnetic Prandtl number. And this is something which was first found by Axel Brandenburg, that the energy transfer to magnetic energy depends strongly on the Prandtl number. It's actually larger for a low Prandtl number. And in this particular simulation, this is a simulation which only has numerical diffusivity. So this is a numerical Prandtl number which I achieved by essentially using more and less diffusive schemes for the momentum versus the induction equation. And I roughly can vary it between 0.1 and 10. And you see it significantly changes the amount of energy extracted from this available energy. And already for a Prandtl number of 0.1, it gets pretty close. The sun has a magnetic Prandtl number of about 10 to the minus 5 in the photosphere, but it quickly increases to values of 10 to the minus 3, but one would expect likely the curve would be very close to the black one. Then one can estimate just in these uppermost 1.5 megameters, it's a third of the solar luminosity, which is actually required to maintain the magnetic field. And if you extend this deeper, it's even more than that. There's a lot of energy involved, and you might wonder, does this have any influence on convection? And this is a simulation which was done a while ago by Hideyuki Hotta. This is stratified convection simulation. Here it has a closed bottom domain, and it's, I think, density contrast of a few hundred. And he compared here a purely hydrodynamic setup also with a saturated small-scale dynamo. And what is shown here is the entropy field. And you kind of see here that there's less horizontal mixing when you have a strong magnetic field. You get these more confined downflow plumes. So in some sense, having the small-scale magnetic field in the system makes the system behave a little bit more like high Prandtl number thermal convection, which naively one could kind of interpret that having the Maxwell stresses around, they mimic to some degree viscous stresses, since they are mostly you get the feedback from the magnetic field in regions where you have a lot of shear flow. Okay, that brings me to my conclusion. So the deep recirculation is necessary to explain the observed level of quasar magnetism, but just going beyond just a single number to compare with observations, it has other consequences, like the deep recirculation leads to large flux imbalance. Since having stratification, magnetic field is brought up from deeper layers, that automatically leads to horizontal expansion, which introduces larger scales even in the photosphere. if one looks at very small scales, smaller than granules, we, in particular looking at these exploding granules and newly forming downflow lanes, we can further constrain this by future observations which look at the deep photosphere at high resolution, where you can kind of disentangle the contribution from deep and shallow recirculation by comparing how much of the feed is organized in coherent thin sheets and how much really appears to be turbulent. Energetically, the small-scale dynamo is significant. It's likely integrate over the convection zone's solar luminosity, or a significant fraction of it, which goes in there. And that means that even though this magnetic field might appear in strength insignificant, there's a lot of Maxwell stresses coming from the small-scale field, which might, to some degree, emulate viscoelastic effects. So actually, the magnetized convection zone behaves more like a high Prandtl number fluid, even though if you look just at the physical values, the Prandtl number of the convection zone should be 10 to the minus 7. I mean, the thermal Prandtl number. Thank you.
And so is the explanation that it comes back as magnetic dissipation?
Of course. I mean, if you wouldn't have the small-scale dynamo, all these would, in the end up as viscous dissipation. It's just part of it you put into magnetic energy, and then it goes through ohmic dissipation.
Subsurface then?
Yeah.
A small fraction goes up into the upper atmosphere?
Yeah. But most of it is dissipated in the convection zone, yeah.
Other questions?
Axel, there's one talk.
Where the large-scale flux imbalance comes from? From the seed magnetic field, or?
So in these simulations, the seed magnetic field, I use just a random field. Each pixel has a different random value. I mean, it's uniform vertically, but horizontally. And the seed field was 10 to the minus 3 Gauss. So the flux imbalance has nothing to do with the seed. It's part of that. You have a, so 18 megameter deep domain means you have a density contrast of 10,000. So magnetic field, which might be small scale at the bottom part of the domain, by the time it's brought up into the photosphere, there's a lot of horizontal expansion involved. And this leads to these smaller bipolar flux emergence events, which then cause the larger scale flux imbalance.
Other questions, please?
I have a really general question. So you have a kind of grid scale diffusivity operating here. How do you enforce a Prandtl number, magnetic Prandtl number of a particular value?
I mean, I don't enforce it as a particular value, but after I ran the simulation with having these different diffusivity settings for the momentum and for the induction equation, I estimate what is the effective numerical diffusivity of the code. And the way I do it, I keep track of what is the numerical viscous, numerical resistive dissipation. If you divide that by a J squared, you can get some equivalent diffusivity. Do the same for the momentum equation. Then the ratio of the two I use to define the Prandtl number in this case.
To what extent is that concept actually in the corona contrary to what normally people are thinking? They think of current sheets making most of the dissipation, and now if it's really viscous dissipation, it's a very different paradigm for heating.
I mean, the corona, I mean, the magnetic Prandtl number of the corona, I mean, if you at least take Spitzer values as a reference, should be 10 to the 10. So that's quite different from the convection zone, yeah. In that case, I mean, you still have current sheets, but the point is if you have reconnections, the direct ohmic heating in these reconnection sites is insignificant. You drive post-reconnection flows which form shocks, and through that process, in the end, you actually dissipate the energy.
Even in the corona, yeah. So, Yuri.
Yes, could you mention how you choose parameters within your slope-limited diffusion when it comes to the induction equation or the momentum equations, and what insight do you have for the rest of us?
I mean, I likely have to put a lot of equations to show exactly which parameter I change how. But I mean, in general, we try to run, of course, the code at the lowest possible diffusivity we can get away with without risking numerical blow-ups. But I mean, in this particular experiment, of course, where I wanted to address some Prandtl number related questions, then I tried to make, in the one case, the momentum equation as diffusive as I can, and in the other case, I try to make the induction equation as diffusive as I can without getting an underexcited dynamo. So this is, I mean, this was just an experiment where you have certain knobs and you just push them as far as possible to the two opposite directions as you can.
Any other question? If that's not the case, then let's thank Matthias again. The next speaker is Frank Stefani, and he will be setting up his computer. We'll be talking about the Dresden project liquid metal experiments on dynamo action and magnetorotation and stability. Please.
Okay, thank you very much for the kind invitation to come here to Boulder. In the next 25 minutes, you will see a lot of steel and concrete, but still we are, of course, motivated by astrophysics, and we always strive to get some cross-fertilization between experiments and theory, and that's why we are doing also a little bit theory, not on your level in the numerics, but we try our best. So I will structure my talk in the following way. The first part will be devoted to the dynamo effect. So there is a velocity which can produce a magnetic field. The second part is connected to the magnetorotational instability, to the Taylor instability. This means we have a flow which is hydrodynamically stable, and magnetic fields can surprisingly make those flows unstable. Those two parts, first and second, I think this is quite solid science. The third part, here I come to the concept of the, where both the dynamo and the instabilities are coupled. This is the MRI dynamo, what we heard this morning from Amitava, and also the Taylor-Sproyd dynamo, and I will come to this coupled system in my third part, and this will become a little bit astrological, if you like. So the motivation is, of course, on the dynamo side, we have planetary dynamos, we have stellar dynamos, galactic dynamos. These are produced by the homogeneous dynamo effect. And on the other side, we have heard a lot about the magnetorotational instability, which is extremely important to explain some parts of cosmic structure formation. So here's a recent survey book by Rüdiger Kicciardino von Hollerbach, Magnetic Processes in Astrophysics, 2013. And we are a little bit proud that on the cover page here, you don't see a star or a galaxy, but you see one of the experiments. And this is our PROMISE experiment in Rossendorf. So the last 20 years have seen quite a whole industry of experiments, the Riga dynamo, Karlsruhe, VKS dynamo, a lot of experiments on magnetic instabilities. This gives you a sort of impression here. And we would like, with our Dresden project, to continue this line of research and drive it a little bit to the extremes, if you like. So Dresden means Dresden Sodium Facility for Dynamo and Thermohydraulic Studies. It is essentially, and I'm very happy that this building is now ready, a new building here. And you see here's a view inside. We have a total of 500 square meter of laboratory area. We have a total sodium inventory of 11 tons. We are planning in the large experimental hall, which is approximately here, a big MRI experiment, a sodium loop. We plan to have experiments on liquid metal batteries, some nuclear-related stuff, perhaps even a Rayleigh-Bénard experiment in later times. And the biggest experiment will be situated here in this reddish one in this containment, and this is a precession-driven dynamo experiment. Here's a general scheme. You see again the precession-driven dynamo experiment to be situated here in this containment. You see here the MRI experiment, a loop, and some in-service inspection experiment. Let me come now to the details of my first part, to the dynamo. So why do we always need this strange sodium, and why experiments have to be so large? So you know that the condition for magnetic field self-excitation is that you have to have a magnetic Reynolds number in the order of 10 or better 100 or better 1,000. This means Rm should be at least 10. And sodium is known to be the best liquid conductor with a conductivity of 10 up to 7 Siemens per meter. And this means in turn that the product of U times L must be in the order of 1 square meter over 1 second. So typically you have a vessel of that size with a velocity of 1 meter per second. This is barely enough to drive a dynamo, and this gives approximately the product of U times L. So of course one might ask, why not making it small and making the velocity high? And the reason for this is that you know that the necessary power in the turbulent regime scales like Reynolds cube over the length. And this means you must have a certain compromise, because this 1 over length forces you to make those experiments not too small. So you will always have experiments of the size of a meter to get a reasonable low motor power of a few kilowatts. Okay, so a little bit history. You might have seen this several times. The Riga dynamo experiment. Here it is based on the Ponomarenko dynamo concept, but then it was made more sophisticated by Agris Skylitis. Here you see the machine, 3 concentric tubes, and here is the computed magnetic eigenfield, which is expected to come out here. The first experiment took place in November 1999. We indeed observed for 15 seconds at least a self-excited magnetic field, and then we had to switch off the experiment for that reason. You see here a little fire, some sodium came out of the bearing here, and we had to stop the experiment. And you see here some sodium oxides and hydroxides in the next morning. So we had to stop this experiment for half a year. And then we could continue with the experiment. Here is one of February 2005. You see that we can switch on and off the dynamo, the magnetic field, by will, and by going up with the propeller above and below the critical rotation rate. So we have done, of course, a lot of numerics and simulations for this, both on the growth rates, frequencies, and the structure of the field. You see here a comparison of the growth rate and the frequency. In general, in the kinematic regime, we are something like 5% accurate to what we simulated before. In the saturated regime, it's also not so bad. We have a reasonable idea about the saturation mechanism. So I think the Riga dynamo is a well-understood dynamo experiment. At the same time, the Karlsruhe experiment became operative. This relies on the concept of a 2-scale dynamo, a sort of alpha squared dynamo, if you like, and it was realized by taking 52 little spin generators, letting a sodium flow go through, and then what the people observed in Karlsruhe, and which was also simulated by Karl-Heinz Rädler and other people, is that you get independence on the horizontal and axial velocity component, a nice dynamo or no dynamo. In 2006, the von Karman sodium experiment, which produces a S2T flow in Dudley and James terminology, became operative and produced a wealth of great dynamical effects, including oscillations, reversals, bursts, localized fields. You see all these effects here, depending on the ratio of the 2 propeller rotation rates. Despite the fact that it worked only if the propellers were made of a high mu, a magnetic material, and it took us some time to understand why is this. And I think those high mu impellers play really a big role in the selection of the mode component, of the dynamo mode, and in the low critical RM here. At least what they have found in Cadarache was a very nice effect of a sort of reversals. As you see here, they are even reminiscent a little bit of the Earth's magnetic field reversals. And this brings us now to our experiment, the Dresden precession experiment, because one of the geophysical motivations is here. Of course, we cannot build a bonsai geodynamo. This is absolutely impossible. But at least we have the motivation that it is well known that some of the parameter changes of the Earth's orbit, including precession, nutation angle, and the obliquity and eccentricity of the Earth's orbit play a role for the reversal statistic of the Earth. Here's a paper by Consolini and De Michelis in PRL 2003, who showed that you have maximum, in the probability density, you have maxima of n times 95 kiloyears, and 95 kiloyears is well known to be the Milankovitch cycle of the Earth's orbit eccentricity. This means those orbital parameters, they play a certain role, if not for the energetics of the geodynamo, but at least for the reversal process, and this is one of our motivations. There are recent discussions about precession for the lunar dynamo. There are discussions about precession in the dynamo in asteroid Vesta, and this might be enough for motivation to do the following experiment. Our experiment is not a sphere, it's not a spheroid, it's a cylinder for some reasons. It's supposed to have or it will be a cylinder of 2 meters diameter, 2 meter height, containing 8 tons of liquid sodium. We plan to go to a cylinder rotation of 10 hertz, maybe 9.5, depending a little bit on safety issues. We have a motor of some 900 kilowatt to drive this rotation, even in the turbulent regime, we hope. And we would like to have a turntable rotation of maximum 1 hertz, so that we can achieve a magnetic Reynolds number of 700. The challenge here with such a machine, with such precession, is that you get a huge gyroscopic torque, which amounts to something like 8 or 10 million Newton meters. This is like a weight of 500 tons on my left arm pushing down, and another 500 tons on my right arm going up. And this turns around, and you can imagine that this makes a lot of load onto the basement. So this is the plan that we have for our experiment. We hope to have first water experiment in late 2019, but you know, schedules are schedules and reality is reality. So let's see. So I talked about this challenge to have connected with the huge gyroscopic torques. Because of that, it was needed to drill 7 deep holes into the soil. It was done in 2013. Here you see the formation of the construction of the ferroconcrete basement. Here you have now a look into the containment with this tripod. And here is a little video from this year, from March, where the underframe was put into the containment, underframe of 28 tons weight, transported by a crane of 25 tons. Don't ask me how this was done, but it worked. And now this underframe is really installed here. Here is the big ball bearing for the turntable. It will be installed soon. Here is our central vessel, which is welded. This is not the newest state. We have already some more specifics here done. This is our 900 kilowatt motor for the rotation. It has been tested. I think it will run. We have, the tanks are there, including some 11 tons of solid sodium still, and the design of the piping system is done. So all this will also be ready by the middle of 2019, I hope. We were forced by the agencies to do a lot for safety, so we installed a big liquid argon extinguishing facility. It was tested, so we are able to bring down the oxygen content within 2 minutes until 4%, which is nicely enough to get all fires extinguished. Here, so okay, now let's come to this was steel and concrete, now let's come to the science. This is simulation done by André Giesecke. The numbers which are given here are always the precession ratio or Poincaré numbers. This is a ratio of turntable rotation to cylinder rotation. And you see here, if this is very, if this is very, if this is small, so we have our first Kelvin mode, then we get our triadic resonances with M4 and M5. They get much more complex, and approximately here, at those precession ratios, the flow becomes completely turbulent. The main question is now, will it be a dynamo? Of course, this was not clear, or is not yet clear. We were motivated by simulations by Caroline Noor, pointing to a critical RM of 600 approximately. We got recently in a PRL paper a quite encouraging result, because we could show that in a quite narrow region of the Poincaré number, what we observe is an additional axisymmetric double roll structure. And this gives a nice dynamo. And the reason for the occurrence of this double roll structure seems to be that at that Poincaré number, you get a modified rotational profile, and this becomes really unstable. And this makes these two rolls. And now we have a simulation for the dynamo, and this gives us a prognosis of something like a critical RM of 430. We have 700 available. We are not quite sure whether we can extrapolate to very high Reynolds numbers, but at least we are quite optimistic at this point. I come now to my second part, to the MRI and Taylor instability. I think you have heard a lot about the background. We have central objects, protostars, black holes, and we have this old problem, how is it possible that the accretion disks around them can become unstable, because angular momentum is increasing outward, so Rayleigh criterion is not fulfilled. And what people now believe is that the MRI could help here. So here is a scheme which goes back to the old paper by Evgeny Velichov in 59. So here is the green one. It's always unstable. Here it is always stable. Also, I come back to this point in a minute. And here is a point where Keplerian flows belong to, and this is where MRI is thought to be important. So Velichov and Balbus-Hawley, they were dealing in most cases with the so-called standard MRI, with a purely axial magnetic field, which requires a high Lundquist number and a high magnetic Reynolds number. And it came as a big surprise when Günter Rüdiger and Rainer Hollerbach showed in 2005 that all the scaling changes dramatically if you add to this axial magnetic field also the azimudal magnetic field. Then we are speaking about the so-called helical MRI. And then this is governed now by the Hartmann number and by the Reynolds number. And learning this, we immediately started to build our PROMISE experiment, which works not in this case with liquid sodium, but with gallium indium tin. And you see here a typical experiment. We are working in a really stable regime, and here we have applied already an axial magnetic field produced by this yellow coil here, and then we are cranking up the current in the middle, which gives us an increasing azimudal magnetic field. And as you see here, this is the traveling wave of the helical MRI appears only approximately at 5,000 amps current through the middle, and we have good correspondence in several parameter variations between theory and experiment. In the last years, we were focusing more on what we call now the azimudal MRI, with a pure azimudal magnetic field without any BZ. And then what you get a M=1 instability, but essentially the same scaling parameters. You have the same Hartmann and Reynolds dependence, and we were more or less successful in in doing experiments until 20,000 amps of central current, and we have a reasonable agreement again with our numerical simulations here. Let me come now a little bit to the Taylor instability. I will later speak about the Taylor-Sproyd dynamo, but first of all to the Taylor instability. Astrophysical motivation is, of course, Taylor-Sproyd dynamo concepts, but also structure formation in cosmic jets. We, as a technical department, we are also interested in liquid metal batteries, where Taylor instability might be a limiting process for upscaling of those liquid metal batteries. We have done, and here's a paper by Sallmeyer in 2012, an experiment with currents up to 8,000 amps through a column of gallium, indium, tin, and we got also, it was much harder than we expected. We got a reasonable agreement between experiments and numerics here in this case too. What are the plans now for Dresden? We will build a large machine of the size of the Riga dynamo approximately, where we would like to combine all our activities on MRI and Taylor instability. And of course, the holy grail of all this will be to go into the direction of studying also standard MRI. But for getting standard MRI, you have to have a large Reynolds number in the order of some millions. You have to have a large Hartmann number in the order of 1,000. But we would like to have also a central current through the middle so that we can start from the well-known regime of helical MRI and then cranking up Reynolds and Hartmann and going down with the B phi in order to try to reach the realm of standard MRI too. So here is the more or less final design of the experiment. You see it's also a huge machine, and here is one of the technical sophistications. We have installed developed a magnetic coupler in order to have no problems with the ceiling or whatever. Here was a first test of this. You hear the machine a little bit, a first test going up to 1,000 RPM. This test was not successful. We get a big crash here, and I was jumping away because it really, some sparks were flying around. And the reason was that one of the magnets, as you see here, was getting loose. And now repair is finished, everything is fixed. I think this magnetic coupler is working by now. Let me come for 5 minutes to the question, which I already indicated here, on positive shear flows. Positive shear flows apply, for example, to the equator near parts of the tachocline. And it was thought for a long time that those positive shear flows are more or less always stable and could not even be destabilized by the MRI. Last year there was a paper by Deguchi who showed this is not true. At some very high Reynolds numbers in the order of millions, you can destabilize even flows with positive shear. It's non-axisymmetric instabilities. But of course, we are looking now more for magnetic possibilities to destabilize flows with positive shear. And the first indication of this came shortly after the Hollerbach-Rüdiger paper by Wei Liu, Jeremy Goodman, Hantao Shi in PRE, who showed that for this helical MRI, there is not only a lower limit of negative shear, beyond which it can be applied, but also an upper limit, which is quite large, approximately 5 in terms of the Rossby number. And together with Oleg Kirillov, we were able to show that these two limits, the positive one, the upper Leo limit, and the lower Leo limit, are really connected by one analytical formula if you allow to have also some current in the fluid, not only a current in the middle, but also in the fluid. And Oleg Kirillov was able to find such an analytical connection, which formula which connects the lower Leo limit with the upper Leo limit. I would like to present one slide about a recent result we have obtained with Georgi Mamatsashvili, which I really like. The point is, oh, sorry. Until recently, it was not known what is the physical explanation for the existence of the lower and upper Leo limits of the helical MRI. And George Mamatsashvili was able to show a quite deep connection, I believe, between the non-modal growth and the growth rate, the linear growth rate of our double diffusive instabilities. And you see here in this plot here on the right side, you see the growth factor of the purely hydro case. And on this side, you see the growth rate of the linear helical MRI. And you see that both are really, really extremely similar. And this might explain, I think, the existence, because the numbers are here exactly the same, of the upper Leo limit and the lower Leo limit. So we have a reasonable explanation for the fact that even very steep positive shears can be destabilized by dissipation-induced instabilities. I have to speed up a little bit and have to say that not only super helical MRI for positive shear exists, but also super azimuthal MRI we have shown with Oleg Kirillov in WKB, and this was even confirmed then in 1D simulations by Günther Rüdiger. Now we have to check, can such an experiment on magnetic destabilization of positive shears be done in an experiment? And the answer is now yes. We have to go to a configuration with sodium and with copper walls. Conductivity plays a big role. And then it seems that we need only a central current of some 33 kiloamps in the middle to destabilize positive shear flows by a pure B phi. And we hope that we can do such an experiment also in the framework of Dresden. I would like to spend the last 5 minutes perhaps with some astrological part. And this has to do with the solar dynamo. And the astrological aspect is here that it had been observed by quite a couple of researchers, starting with Rudolf Wolf in 18-something, whatever, and Bollinger and Takahashi and Wood, and that there is an amazing empirical synchronization of the 11-year cycle of the sun with the spring tides, if you like, with the alignment of the tidally dominant planets Venus, Earth, and Jupiter. And I can show it here. So here is the cycle number, here is the year. If you take the cycle minima by Chauvet and Hathaway, the red and green ones, and put them here, and you take the maximum Venus, Earth, Jupiter alignment like this, you see nearly the same curve. If you take now the residuals, so the values here minus the linear trend, you get more or less two curves which are really straight. It never goes out of phase, so there is an amazing synchronization. And I think it's worthwhile to ask, could there be any physical reason for this, or is it a pure accident? It was Dicke, it's a guy from the Browns-Dicke theory, who had a Nature paper in 78, and Dicke had a very interesting argument at this time. He was taking a time series, and he was trying to distinguish between a random walk process and a clock process. And he defined a very, very nice measure, a very nice argument, and I would call this Dicke's ratio. And this is the ratio between the mean square of the residuals themselves over the mean square of the difference of two subsequent residuals. And for a random walk process, if you take the starting year here and you take the n, this should go in the limit to n over 15. For a clocked process, this should go to a value of 1/2. And now I took the data from Chauvet. I know it's disputable if we can take the data from Chauvet for the solar minimum. But if you take them, you see that those data of Chauvet, even 1600, which is quite safe, and here they're becoming a little bit worse, but they never go to a n over 15 line. They seem to approach even a 1/2 line. And I think this is a strong argument in favor of the fact that there might be a clock for the solar dynamo. Now, let's try to make a sort of theory about this. you know better than me that you need, for a dynamo, a solar dynamo, you need an omega effect, which is trivial, but you need also an alpha effect. And I would like to focus in the next minutes on the Taylor-Sproyd dynamo concept. So the idea was you have your omega effect, this winds up a certain strong B phi, this B phi becomes unstable to m equal 1 Taylor instability, and by some mechanisms this might close the loop. This concept had been criticized by Jean-Paul San and colleagues in a 2007 paper by saying, so this does not work, because if you wind up m equal 1, you don't get your toroidal field back. But at the same time, colleagues said, if you have an alpha effect connected with a Taylor instability, this might give you a chance to close the dynamo loop and to make a Taylor-Sproyd dynamo running. When dealing with a Taylor instability, so we were working always in the low PM limit, and what we observed was a funny tendency of the Taylor instability to develop oscillations of the alpha effect. And I would like to show you a little video which shows you the physical character. Sorry for the gap here in the video. So you have a Taylor instability like this, and this helicity oscillations, they correspond to a sort of tilting, and this is an intrinsic process. Well, what is it good for? Now, imagine you have some planets making a tidal forcing. Tidal forcing is always m equal 2. And now imagine an m equal 2 forcing of a m equal 2 forcing. And what we observed then, that you get a strong resonance of this external m equal 2 forcing with the amplitude of your alpha effect of the Taylor instability. So you can, by external m equal 2 forcing, synchronize your alpha effect. And then it's not a big surprise, if you can synchronize the alpha effect with the m equal 2 forcing, you might get a synchronized entire dynamo here. Here is some new simulations. We tried a 1D Parker migratory model. Please look at this. This is a B field. What you see here is maybe not a perfect butterfly, but it goes in the right direction. This butterfly, I hope that I can still improve it, and you get the perfect 22 years cycle here. What we also get, it's a funny thing, we get even in the northern hemisphere, we have a dominant positive helicity, but also some negative helicity, and this is reminiscent to what has been found by Shang and Kusanyan and other colleagues. We very naturally observe the second peak, which is always, if you take the north and south polar field here, we observe it always in our simulations. It's very, very intrinsic to our models. We can very, very simple switch, sometimes even spontaneously, but if you change some parameters, we can switch between the dipoles and the quadrupoles, and this is reminiscent to what Rainer Arlt and Nigel Weiss had observed after the Maunder minimums, that you might even get a quadrupole field here. Yeah, this is maybe still very speculative, but we see a certain chance to synchronize the solar dynamo by weak planetary forcings. Of course, people say this is completely rubbish because the tidal height produced by the 3 planets is 1 millimeter, which sounds ridiculous. But if you take the energetic equivalent as a velocity, this 1 millimeter corresponds to 1 meter per second. And I think this is not ridiculous at all. And this might really give us a chance to synchronize it. It's a funny thing we have observed. This is really a subcritical Taylor-Sproyd dynamo. This is a very recent result. You see here the strength of the periodic alpha term, and here you see the amplitude of the initial condition. You see here this tethered stability boundary, which is very, very typical for all subcritical instabilities. So this is a special effect here of this Taylor-Sproyd dynamo. And maybe that's it for today. Thank you very much.
Questions?
Thank you for this very interesting talk. I would like to go back to this point regarding positive sheared flows, where you mentioned that you want to explore the azimuthal MRI. There is one thing you might run into, which is that positive sheared flows are known to undergo a subcritical instability at Reynolds number around 1,000, which might spoil the azimuthal MRI. So can you comment on that? Do you know how to avoid it?
Yeah, I think I have shown this one slide showing the connection between the non-modal growth and of the pure hydro case, and it was pure hydro what I showed, and then the growth of the linear instability if we have the helical MRI, and there was a strong similarity of the two curves here. Still, if you have Reynolds a few thousand, in our case the Reynolds number for the super AMRI, as we would like to call it, is not very large. So it's in the order of thousands. So I'm quite optimistic that we can overcome those pure hydro non-normal growth things. But there is still a deep connection between both.
So coming back to this deep connection between the non-normality of the hydro and the magnetic yes. results, can this be demonstrated by looking at the eigenvalues of the resolvent operator? Is that how you do it?
Perhaps. So what we did, we analyzed really the WKB for everything, and then we get the analytical formula here. So it's really WKB. But it can also be shown in a 1D simulation. But the results are in WKB, they are exact. And these relations which I showed, these are exact relations. It's a PRE paper 2 years ago, I can show you.
Any other questions?
So some stellar observations show a relationship between stellar cycle periods and the rotation period of the star. That wouldn't jive with any explanation based on planetary orbits. What do you have to say about that?
We were looking a little bit into the data. I'm not an astro guy, so to say. We discussed with Ray Bolo and other people, and of course it's always interesting. The point is always, is only you need to have all the planets. Because in our system, if this is true, I'm not sure. Venus, Earth, Jupiter. In most planetary systems, you see only the Jupiter. You wouldn't see the Earth and the Venus. But you need all of them because the tides, they are going with 1 over r cube. M1 over r cube. And you always need all the planets in order to check what is the dominant spring tide of the planets. And that's why this argument with other planetary systems, if we would have all the planets, and there are, I think there are a few planetary stellar systems where they know a couple of planets, maybe it can be checked, but I did not go into the data yet. I was focusing on our system. Yes.
If there were planets, they would be an unseen, let's say, hidden parameter that you would expect destroys the correlation if the rotation didn't matter.
Yeah. I do not claim that it would be general for all things, but at least the empirical correlations, the empirical synchronization is, I would say, quite striking here. Perhaps it's an accident, so nobody knows.
Okay, let's thank the speaker again.
Yeah, good.
Go to select. Push some buttons.
Okay, so our last speaker will be Yuri Tomre, who's going to be speaking about magnetism and M-stars.
Oh, we were told something rather enticing earlier, that there's a lockdown because there are bears outside. On the other hand, that might prevent us from having some beer or wine. So what was this all about, Mr. Featherstone? Wow. Bears, even plural. I like bears. Well, I want to talk about in this astrophysical code of M dwarfs, or whatever those things, stars are. And it would be lovely if we could actually see some of these stars with the exquisite sort of resolution that we see of magnetism in something like the sun. But that will not occur. On the other hand, let me just remind you a little bit about the game of astrophysics. Many of you know it, but of course, if we talk about what are some of the guiding principles of stars, the HR diagram, the Hertzsprung-Russell diagram, comes into play, because we would say, look, if we ask where do most of the stars lie, they lie on this basically the main street, the main sequence. If we ask about, well, what's the oomph, how much energy comes out of these stars, they're extremely sensitive to what are the nuclear generation rates. If this is the location of the sun, and we, in this spectroscopic lettering code, call this a G star, where are the M stars? Well, they are here. They're more distinctly redder, but they're also reasonably feeble in terms of their energy output, like 1%. Rakesh told us earlier that we should be interested in these M stars. Why so? Well, you might say we should really be dealing with the much more energetic stars. The ones might be 10 solar masses. They would have about 10,000 times the luminosity of the sun. That's rather nice. They have fairly short lives, and they also blow up as supernovae. So those are neat objects. All of these stars, as you've been hearing, share the property that they have convection somewhere in their business, and they have the possibility of building magnetic fields. Earlier, I can also change, yes. So why should we have some interest in these more feeble stars, which you call the M dwarfs, or main sequence stars? Well, primarily because we're in this great adventure of hunting for exo-Earths, planetary systems. And so the Goldilocks zone is where you think there would be liquid water, at least some liquid something, that might favor habitability or the biological cycles. And the M dwarfs, the M stars, play the following game. Our own galaxy has of the order of 400 billion stars. We haven't counted them, but it's roughly of that order. And by far the largest number of those stars will be the M stars. They have the advantage that they will, once you form them, they'll live forever, effectively. They'll have lifetimes of maybe 10, 20, 30, 40 billion years. You'll build them in abundance. You'll also have the possibility of detecting planets fairly close to them, as we have done with the Kepler mission, for instance. So the ones that have both the Goldilocks properties and their numbers on their side tend to be the M stars. However, there's a hooker with this. For reasons we really do not understand, we can speculate. Very many of them exhibit very strong flaring and repeated flaring. And with it comes gamma rays and X-rays and a few other things that would also make habitability a little bit difficult. So mixed in with these, both the stars being large in number, but also threatening habitability on some of the exo-Earths that we're looking at, we should spend some time trying to understand what is the origin of the magnetism, some of its properties, and Rakesh already introduced the subject to us, and he's been one of the workers on looking at dynamo processes within some M dwarfs. And further, something that is very prominent in almost all stars is that if you were to ask, well, what is the apparent measure of activity, which might be the X-ray emission compared to the total emission from a star versus their Rossby number. So faster rotation moves you here. If you take almost all the stars where we measured it, there seems to be, you climb as you rotate faster and have more and more sort of emission, and then you saturate. If you did this for the K-type stars, or particularly the M stars we're talking about, they're a little bit harder to measure because they're so reasonably faint, but they all seem to share somewhat similar properties. And so of some interest is how do these things come about? The other thing that's present with the M dwarfs is that if we look at, again, the coding that only astronomers love, but basically the more massive M dwarfs, which are about sort of half a solar mass versus something that might be a third of a, or 20% of a solar mass, you have a location where you separate stars that have basically deep convective envelopes and a radiative interior from others that are fully convective. And Rakesh Yadav was talking about some of the fully convective stars. It's quite interesting that the ones that have a deep convective envelope may have a tachocline at the base of it if we go from the solar experience. Very small fraction, maybe 10% of them, show activity. Whereas the ones which are fully convective, most of them, like 90% or so, are active. How has this come about? And one may speculate that basically the current activity also reflects the different spin-down histories that have occurred. That possibly these stars, the ones that are the more massive ones but have a tachocline, experience much more effective spin-down early in their lives, so they're now fairly slow rotators on average. And then that ties into the previous thing we looked at. So let me touch ever briefly on some of the experiences that many of us have had in studying things that are around and that have shells in them. The ASH code was one of them. Now there are a number of global three-dimensional codes, and a number of us have worked on it, including Nick Featherstone. And if you said, well, what's been done with this? Well, a number of stars have been sort of studied in different ways, some fairly extensively, some only briefly, but basically sampling some of the properties across the main sequence. Matt Browning particularly started the game, particularly with some of the M dwarfs. Rakesh Yadav has done at least two fairly recent papers on this subject. Some of us have also studied the more massive stars that have core convection, which at least within those domains tend to build very strong fields. With a B star that's of 10 solar mass, we find that we can build fields of the order of 5 to 10 megagauss, and that may influence the later histories of these stars when they blow up and become neutron stars with much fiercer fields. But common theme in most of this work is that if we go to the solar cases and we look at them in Mulwady views, so the equator is here, the poles are there, and we look at what's maybe going on with dynamos that are operating. There's a fair amount of sort of alignment at low latitudes, Taylor columns of one sort or another. But if we ask, well, what types of fields do they build? They tend to build things that we've come to call magnetic wreaths. And it's prominent in many of these stars. They go through cycles. They have, if we look at essentially the longitudinal magnetic fields as a function of time, they tend to have a fair amount of magnetism at fairly low latitudes, and they chug away, building fields that peak at around of the order of 10 kilogauss or so. And we've come to call them magnetic wreaths. If we cut into these structures, we can see that there's a fair amount of field at low latitudes. These look fairly bland, but if we ask, well, let's look at a cycling behavior in a cutaway, that looks rather nervous. But these are the field lines and the strengths. And systematically, these things go through reversals. Do these reversals capture the solar behavior? Not quite. But they also, with other codes, where at least have some of the machinery with which you can begin to study what happens in coupling systems that have convection that is rotationally constrained, reasonably reduced magnetic diffusivities. If we take some of this machinery and ask, well, this is all going on the inside, are we able to actually get some field to pop up to the surface where our observational evidence is concerned? And the answer is yes. Bits and pieces of these wreaths become unstable, and they can lead to loops that rise toward the surface. We don't go all the way to the surface in any of these simulations for the reasons that Matthias told us about, the great range of scales that intrude upon systems. But it says that certainly these experiments that many of us have been participating in, of trying to deal with essentially computational astrophysics as a way of doing Duncan experiments. They're far from realistic in many ways, but they're highly nonlinear, and they give us some pleasure, and they're motivated by a series of sort of astrophysical questions. So let's get back to actually the M stars. Connor Bice, who is also here in the audience, Connor, working toward a thesis, has turned to a very close relative, but a very modern relative of the Ash code, Rayleigh, built by Nick Featherstone that he spoke about. But again, it's basically an elastic MHD occurring in rotating spherical shells that may go all the way to the center. What we've chosen to do is to look at one of the stars that has, in principle, could have a tachocline. We take a background state for the star from a stellar structure and evolution code called MESA. We take a star that has 4/10 the mass of the sun, and here rotating about twice the solar rate. And we can do some experiments where we can either include or exclude whether we put a stable layer below the convection zone. The profile of this star looks like this. We can't quite get to the surface, and the base of the convection zone would be about here. We might just put a slippery boundary here, top and bottom, or else put a region of penetration into a home-built tachocline and ask what is the significance of it, whether you have a stable lower layer below the convection zone or not. And maybe indirectly we could explore what role a tachocline might have on some of the dynamo behavior. Playing in the background is the radial velocity in one of these simulations that was really run. And again, like with Rakesh, we capture a density contrast of about 150 or 130 across this layer. So it has to be a compressible code, but we don't want to chase sound waves around, and so we filter them out by the so-called anelastic approximation. So when we look to see what comes out of some of these simulations, if we look at the longitudinal B5 fields, say, in the middle of the convection zone, in the absence of a tachocline. So we have a zone that looks like this. I'll tell you what this is in a moment, but the east-west of the longitudinal fields are either red or blue, depending upon their polarity. The same star, if it was to be entirely hydrodynamic, would exhibit a fairly strong differential rotation. You allow it to run its dynamo, and basically wipes that differential rotation out. It's very bland. And so the magnetic field generation is almost entirely by, in mean field theory, you might say alpha squared. There's no omega effect effectively available to you. So it's helical field generation, but it builds fairly strong fields in this M star that we're dealing with. Field strengths typically of the order of 16 kilogauss or so at peak fields. If we ask, well, what do the fields look like if we average both in time and in longitude? It has structures like these, which emphasize, again, we effectively have true wreaths of magnetism that are intrinsic to this. Somewhat in the flavor of the other sort of problems we looked at. If, on the other hand, we also allow there to be a region of penetration below, the behavior at mid-convection zone is very similar to the previous movie. On the other hand, if we ask, well, what do the fields look like in the region of stable stratification? They're much smoother. They still have ripples and bumps. And you might say, well, how is this magnetic field generation occurring? And principally by overshooting and injecting fields from the convection zone in terms of the motions that penetrate into this region. And there's still some weak differential rotation, and that plays some role also in smoothing it. And what is interesting is, again, you're still, even in this middle of this region, have field strengths of the order of 4 to 8 kilogauss. If on the other hand, we march to the top near the top of our solutions and ask, well, what do the radial velocities look like? Well, there are a fair amount of structures that at low latitudes look somewhat like banana cells, and other related fairly fast downflows and upflows in the higher latitude regions. So this happens to be one where we omit the tachocline. The other looks fairly similar. And so what do you get with this stuff? Well, you certainly find that you can build fairly strong magnetic fields. If we look at these time latitude diagrams where we've averaged in longitude and ask as a function of latitude, how do these things vary in time? The behavior near the surface and in the middle of the convection zone. It's quite clear that these are solutions that are cycling, not in a very tidy fashion. There's a fair amount of poleward migration of this longitudinal field. And the other behaviors, even though you have this fairly small region of penetration, as Yuhang has also found in other problems, it's fairly sensitive as to how you influence the cycle periods. You do have reservoirs of field that are in that lower region, and whereas in the absence of a stable layer with a tachocline, you have cycles that are of the order of roughly 100 to 150 rotations in these units. With the presence of a tachocline, the cycle periods are very, very much lengthened. We have more data, but not shown here. So you almost double or so the tachocline plays a role. But one might further say, well, is there any great significance in addition to that? Well, the interesting thing is that by having Here we show, again, the time averages of these mean fields. The longitudinal fields are shown here with no tachocline, with a tachocline, similarly the radial magnetic fields. And we could say, so what happens? Well, it's fairly interesting that when there's a tachocline present and you ask, well, what is the behavior of the axisymmetric poloidal fields, which require information from both of these pieces of information, we find that the dipole, quadrupole, octopole modes have substantially more power when the tachocline is present. That effectively you build larger scale structures by having this reservoir present. Is there a message from that? Well, it suggests that it may be the one point of significance is that if you are one of these more massive stars and emits a tachocline rather than going convective all the way to the center, you may be really improving your ability to shed angular momentum through your magnetized winds. And you need something like this to be able to ask, well, why is it that the more massive stars are essentially showing very little magnetic activity compared to the other ones? I mean, only 10% are magnetically active versus 90% for the other ones. So maybe the message from Condor simulations rests along those lines. And so maybe so far, the takeaway message from at least looking at these M2, the more massive stars, is that I think independently of which M stars you're looking at, they've got sufficient oomph to build fairly strong magnetic fields, and quite a bit of them will be wreath-like. If you have a tachocline emitted, at least in these simulations, you have essentially an additional reservoir which has one effect. It can slow down the reversal of the global fields. But interestingly, that tachocline also seems to promote building larger spatial scales, even though it's far removed. Of course, it influences the linkage of field within the convection zone itself. And this may have the effect of really changing how the magnetized winds remove angular momentum in these more massive M stars. But the overall question, the motivating question for being maybe excited about M dwarfs is the one of habitability. Could you have planetary systems where life could exist? And that really requires asking, well, how do you actually do the flaring bits and pieces? Of course, the building of large-scale flares and sympathetic flares is quite a challenge for our own star, even though we live next to it. But it probably points to having access to codes that Oki was speaking about, or Matthias, where you must not only have the magnetic engines on the inside, you must link them to something which begins to ask, what type of corona can you build? And how is it that these small stars, they're of course, the stars have a lot of much more oomph than planets have, and they also operate dynamos, but what is going on with these stars that they can have major flares that are repeated that might be 1,000 times the energy of the largest flare that we've ever seen from the sun? And in one way we might say, well, look, they're small stars. Do they deserve to do something like this? It's very good that we don't have it here because we probably would not be living on this planet. But in terms of motivation of things that geophysical turbulence and astrophysical turbulence theory will advance toward, it's actually trying to deal with these complete systems and trying to understand what's going on with the M dwarfs. Is it possible that you've ended up building enough field that you're essentially filling the surface of that star? That's a speculation. The sun has only isolated active regions and big sunspot groups. What if you basically populated rather more vigorously? But then what type of corona would you build? And Yuhang may have some opinions about this, or Matthias, but it would be a case of having combined systems, and I hope that things like this will be forthcoming. But I just mostly wanted to remind you of the joys that some of the tiniest stars that we have in our star medley, the implications that they may offer. It's the numbers game. If 70 or 80% of the stars are M dwarfs, and they have the possibility of having Goldilocks zones of liquid something, water may be preferable, and life could emerge, does it behoove us to try to understand what is the habitability of these systems? And flaring seems to play a significant role. So thank you very much.
Thank you. And questions, please. Yes, please.
I was just going to ask, has the actual mean field approach been applied to the simulations just to see what is the source of the EMF?
Well, we're in the thick of that right now. Yeah, but what we do know is there's almost no differential rotation left in these systems. Sure, I understand. We've done so in a different context, which is basically the B stars with core convection, which is building 10 megagauss fields.
Steve.
So Yuri, it's interesting that you seem to have quite a large axisymmetric quadrupole component as well as...
Yes.
Is that different when you have a tachocline to when you don't have a tachocline?
Yes.
Yeah.
Yeah, the tachocline seems to really favor... We haven't run very many cases yet, so we need to understand also how sensitive things are to the magnetic permeable number and many other things. But that seems to be a property of that.
Right, and there's about as much energy in each the quadrupole as the dipole?
Pretty much so.
Okay, thanks.
The dipole is the weakest, but it's the quadrupole and...
Just a quick question, Yuri, sorry. I didn't catch, the ones that do have wreaths, are these fast rotators or are they not fast?
Well, reasonably fast rotators. I mean, certainly for the sun, you need to be rotating about twice the solar rate. But the M dwarfs, the convection is much slower, so that the cases that we studied here, twice the solar rate, are really pretty fast rotators. But I think you can slow them down quite a bit and still have this behavior.
So you showed how the heavier M dwarfs, the ones that have tachoclines, they're not observed to have strong magnetic fields. Do we know anything about...
Only a small fraction of them, yes.
Do we know anything about the Rossby numbers of those, or can you only measure the Rossby number if it already has a strong field?
Well, it's hard to measure the rotation rates of these stars. The trouble is they're also reasonably distant and feeble, but one is beginning to populate the rotation activity curves pretty intensively just because you're finding extrasolar planets around them. It's motivating.
Or another way to ask this is, are there any cases of low Rossby number, more massive M dwarfs that do not have strong magnetic fields? Because that would be a counterexample to what you're suggesting.
The numbers are very small.
Do you actually have any simulations that are fully convective? You compared with and without tachocline, which did not have.
Well, we have some that we had preliminary done a couple of years ago, but we haven't done the detail. Connor is working on that now, and I hope that Rakesh continues to stay in that business and don't be led off by this planetary dynamos. The M dwarfs deserve your attention. Pardon me? Pay me. Well, as soon as we find exo-Earths around some M dwarfs, I think NASA will become even more lubricated in that direction.
You said that the Coriolis numbers are never really very big for M stars.
I'm sorry?
You said the Coriolis numbers are never really very big for M stars.
Well, there probably are some that are very slowly rotating, but it's very difficult to measure the rotation rates of these stars.
So if you were to go much faster, you would eventually find a transition to non-axisymmetric fields as a function of Coriolis number, one would expect.
You might, yes.
But that has not been seen yet, and the dependence on tachocline has also not been mapped out yet.
No, it has not.
All right, if there are no further questions, then let's thank you again and all speakers of today.